All right, so where were we last time? So now stop thinking about the test. Okay? Back to the lecture. So we were working with the normal force, right? So we were working with the normal force and different cases involved in normal force. If the object is placed on a flat surface, the normal force is going to be equal to the weight force. Weight force is downward, normal force is always vertically upward. The normal force always arises due to the surfaces pushing on each other. This is always between the surfaces which are resting on each other. The heavier the object is, more is it going to push on the surface. Correct? And the normal force will be greater. How the normal force is different from the friction? Friction tries to stop the motion. Friction is always active when there is an external force involved. Normal force is there even if there is no external force. Okay, it always comes into play when two objects are just in contact with each other like this. Here there should be a bind force. This book table should have a normal force, and normal force, the most important characteristic of the normal force is it's always perpendicular to the surface. That's why it's called the normal force. And it's not always equal to the weight force. So in this case, when the surface is flat, the weight force acts downward, normal force acts upward. In that case, they both should be equal in magnitude and opposite in direction. Okay? In this particular case, however, when the surface is not flat, there is some external force acting on it. We saw that in previous lecture, that if there is a force applied pulling on it, if there is a force pushing on the object, in that case, there will be a different normal force, right? Correct? So the normal force is subject to change. It's not always equal to the weight of the object. Okay? That is something you should keep it very, very clear in your head. Normal force can vary from one situation to another. The weight remains the same. That doesn't change, but the normal force can vary. All right. So we did the first case. We did the flat surface. We also did the pulling, the application of the force with push and pull. In case of pulling, the normal force is reduced. In case of pushing, the normal force is increased. The equations I gave you, they are in mathematical form. You don't have the numbers in them. But if you have the angles applied given, you just plug those in, those will generate some numbers. But the important part is that how the normal force changes with it. Now, we were going to work on the normal force on an inclined surface. It's not a flat surface, but it's the inclined plane. What do we mean by inclined plane? It has a slope, right? Can we make inclined plane easily? Yes, we can. You just lean anything, you just keep anything at some angle, making with the horizontal. This is an inclined plane. So if you have placed an object on the inclined plane, is it okay if I put the gravity there? We know about gravity already. It should be acting downward, straight down. It should not be at any angle because it's the gravity. It should straight down. What else I should put there? Sorry? Very good. Which way? Is that right? Right? That is coming from the box pushing on the plane. What do you think about the normal force? Should it be less than mg or greater than mg or equal to mg? What comes to your mind? More than mg? Why? Mm-hmm.
If it just pulls straight down, would the box necessarily sit right on top, or does no one have to add extra force?
When it is on inclined plane, is it pushing on the surface the same way it was before? No, slightly less, because it's now at an angle. And you know, if you keep bringing it to a higher angle, what will happen? It will start sliding down, right? Because now there is less pushing on the surface. The normal force is not equal to mg, that's for sure. It's less than that. But we will see how less this is. So the gravity, let's say this angle is theta. Which one of those? So m is not equal to mg, we know that. But which one of those do you think has components involved? Is there any vector that you think that I should have divided into its components, which is not completely vertical or not completely horizontal? It is making some angle, I need to divide it into its components. If yes, then which one? Sorry? It's making 90-degree angle with the surface.
So FG would be separated because relative to the object it's not triple.
Say it again.
So like relative to the object, the force of gravity isn't acting in a straight direction.
Exactly. With relative to the object, it's acting straight down, but it is making some angle. Right? It's not vertical like it was before. So full gravity is not in effect in the same direction. It is in effect in two directions, one x and one y. You need to figure out what that angle is going to be. Can anyone tell which angle is that? What does it look like? This is vertically down, so this should be
It's a right triangle, so if you know theta, then you can get
90 minus theta, right? So since I'm keeping it in this form, I haven't given any number yet. Yes, that would be the procedure to get the angle. 90 minus theta would give you this particular angle. I want to shift this and draw it again here. Okay, so it's the same thing. This is here, mg 90, right? It is something like this, correct? I am taking this line as horizontal. Okay, this time so basically it's a picture upside down. So I drop the perpendicular on this. mg cosine 90 minus theta is equal to, here mg sine of 90 minus theta. Right? Horizontal component is cosine, vertical component is sine. Okay, this is whole thing upside down. Okay, my horizontal is here, with which mg is making angle 90 minus theta, and then I divide this mg into its components. This becomes cosine of 90 minus theta. I hope everybody knows it is equal to what? Sine of theta, correct? 90 minus theta, sine changes. So mg sine theta, this becomes mg cosine of theta. So in this case, what you used to have for the horizontal component cosine of theta, it's not cosine anymore, it's sine of theta. So we have two components now. This one is acting along the inclined plane. This one is acting below the inclined plane. So they are here. So if I draw them here, they look like this. This and this. mg sine of theta, mg. Okay. So what did we do here? Our mg is not vertically straight down. It's making an angle. What angle it's making? We figured that out. It was 90 minus theta. Then we divided into its components. Cosine of 90 minus theta changes into sine of theta, and the sine of 90 minus theta changes into cosine of theta. One is below in this direction, one is to the right. This is to the right, this is below. So this picture is now complete. We have divided our gravity into its components. Now maybe you notice that instead of putting Fg, I have put mg there. Okay, it is from this. Where does this come from? When F is equal to ma, when it's the weight force, then acceleration is the gravity acceleration. Okay, so you could use the Fg equal to mg. Sometimes the W is also used for the weight. Weight, Fg vector, mg, they all represent the same thing. Okay, so Fg, W, mg, they all represent weight. Okay, so where you have Fg, you will have to replace it by mg because if mass is given, you need to multiply it by 9.8 meter per second square and get the weight value. Good so far? Is this picture pretty? I think I did a good job there. It's a bit complicated, but try to do it from scratch. Okay, do not follow the same pattern I did. Try to do it from scratch when you rework your lecture. So you have two components. One is to the right and this one is to the bottom. Now if the object is not accelerating, then horizontal acceleration would be 0, right? It's not accelerating. It is sitting there and probably balanced with something. So we haven't mentioned the friction force yet. There must be some friction force acting on it too. We will add the friction force once we introduce friction. But there is no acceleration there. But are there any forces which have balanced each other vertically? How about Ay? Is there any vertical acceleration? Is it moving up or down? No. What does that mean? All the vertical forces have cancelled each other. N good. N is up, so positive. Mg cosine of theta down, so it's negative. There is no acceleration. This is 0. N minus mg cosine of theta. or N is equal to mg cosine of theta. Has normal force changed? Has normal force changed? Yeah, it has changed. Is it less? It's not just this, like a flat surface. It's component. Whatever is its component, opposite to it, the vertical component, it's equal to the vertical component of the weight. Or just right here, it is equal to the vertical component of weight. Okay. It's equal to one of its components. It's not equal to mass as a whole. All right? Good? Okay.
So what counteracts the horizontal component of it?
This? So this will be responsible for its motion. So when it slides down and has a horizontal acceleration, this component will play a role. Okay? We will revisit it.
Okay, so we're just ignoring
Right now, yes, right now. Right now, our emphasis is the normal force. And in this case, the normal force is equal to. So, but if the box slides, mg sine theta is involved. Mg cosine theta has nothing to do with the box motion because it's balanced upward and downward with the normal force. Okay. Another example of the normal force is have you ever been to elevator? Very often, right? Several times a day. Does it accelerate? Does that accelerate? If you put a scale inside or the weight machine and step on it, it reads something. What does it read? Your weight? Are you sure? What if it's moving? Is it going to read something different other than your actual weight? But it does. It does. Apparently the weight changes. How do you feel when you are going up? Heavier or lighter? Heavier. And when you are coming down, you feel lighter, right? It's a feeling. It doesn't mean that you are shedding off pounds in there. Okay? That's true, right? So mass is not changing. Weight doesn't change. But apparent weight can change. So your scale does not read your weight. It reads the normal force as long as the elevator. So I'm going to draw the elevator. And then there is a scale. If you step on that scale, your weight would be down and the normal force would be upward. The normal force is what the scale reads, okay, and normal force is what changes when the elevator goes up or down, okay. So if you have a real scale in there, it should show you a different reading while going up or down. So let's do the case in accelerating object. Let's do the case where it's going up. Okay, so your elevator is going up with some acceleration. Sorry, A is positive because it's going up. The weight of the person is downward, it's negative. Normal force is upward. Good? So far okay? All right. We are not looking from anything from the outside world. This is our world inside the elevator. Inside the elevator, you are standing on the floor of the elevator. You are pushing down on it with your weight, and the elevator pushes back up on you with the normal force. There is some acceleration which you all are experiencing, you and the elevator, and that is A, and it's upward. Yes?
Would the speed of the elevator affect anything?
I mean, it's accelerating, so that means the speed is increasing. It's not going with a constant speed, that's why it has the acceleration. Right? If there is no acceleration, then there is no change in weight. Then it's a uniform speed. Okay? This will only happen if the elevator is accelerating. Then it will make changes to the normal force. Then you are going to feel heavier or lighter. Otherwise, no. It would treat you same as rest for the uniform motion. Okay? So we start with the. Are there any horizontal forces on me standing in there? No. Are there any vertical forces? Yes. What are they? Go ahead. Positive or negative? Positive. And anything else? No. You don't put acceleration there because this is the net acceleration of the system. So this goes in here. F equal to ma n minus mg. There are no other forces. That's all the body has. Okay, clarify this too. Don't put acceleration for the rest of it. Acceleration is for a system. Okay, so everything in it has this acceleration. It's the overall or net force or net acceleration. You don't put it with rest of the rest of the forces. Okay, it's the net force. Okay, it's the net force which is coming due to these forces. Okay, so I'm going to rearrange the equation. N would be equal to ma plus mg, or taking m common, a plus g. By how much? By what factor your n would go up? By ma, right? So is your normal force higher? Is your normal force higher? What makes you think that? You are adding something to it. Yes, it is higher. By what factor? By the acceleration and the mass. Okay, more it is accelerating, more change in the normal force would take place. All right? The normal force would be greater. Okay, so I should draw an arrow which is longer than my mg, because my mg and my ma, they add up to make that normal force. Now, obviously, we did this, so we should do when it's going down. Can you guess what should happen? It should decrease. Yeah, that would be our first guess. Mathematically, going down, you will have a negative acceleration here. Right? You're going to have negative ma here. The rest remains the same. Everything else remains the same. You move things around, this is going to end up as mg make minus ma. G minus A. Okay, so your overall apparent weight will change. Okay, remember that we are not saying that the weight will change, it's the apparent weight will change. Say it again. Because it's going down, because it's moving downward, yes, yes. And that would change everything. It's very critical that you put the signs with it. Because if you don't use a negative sign, there is nothing else which is telling you that the normal force is decreased. It's because of the negative acceleration. So gravity is already acting downward. Okay, elevator is moving downward too. So doesn't need enough normal force to support it or balance it. That's why it's decreased. Because there are enough forces always already acting in the downward direction. So there is always a reason behind it, why it has increased, because there was not enough normal force to balance it out, so it went up. So when it is already going down, gravity is downward, normal force, the acceleration is downward, normal force doesn't have to be that much. Let me give you a problem, okay? Because now you know how important this is, that we know how to solve the problem. Now put some number to it. We are going to put some numbers to it. The mass is given. The elevator descends and accelerate at 0.2 g. So she is stepping on an elevator, she is stepping on a scale placed inside the floor of the elevator. Her mass is 65 kilograms, and the elevator accelerating or descent means it's going down at the rate of 0.2 g. What does that mean? What do you think what that could be? Exactly. G is, it could be used as the unit to represent the acceleration. Okay? Sometimes you would see the acceleration as a multiple of G. So don't get confused. Don't think it's grams. It is still the acceleration, but given in terms of gravity, acceleration due to gravity. So you want to know what is her weight during the acceleration and what does the scale read. Go ahead, do it. First, try yourself. Yes, and mean it's negative. Yes. So 0.2 G is going to be negative. Mm-hmm. You need to multiply it by 9.8.
Okay.
That's it. That's the actual. So G should be in there.
Okay.
Okay. Mm-hmm.
I don't know if I used the right formula.
No, no. So it's straight up. There is no angle involved. Okay. Downward force is mg, upward force is n, and negative 0.2 g times the mass is the acceleration. So use what we just did. Where is the elevator equations?
It went back too fast.
Oh,
I didn't get it.
oh, okay. Then wait for it. Five or nine? Yeah. So it's different from the actual weight? Is it different from the actual weight? What is the actual weight? W is equal to m g, 9.8. What is it? Say it again. 637 Newton. Correct? That's the actual weight. When the elevator is not going anywhere, when the normal force is, the scale would read this number. Now during the acceleration, the weight, we already said that the weight does not change. It's the normal force which changes. So we have to figure out what the normal force is going to be. So if you want to draw the picture to go with it, so it's her and the weight is down, normal force is up, this descent down, minus 0.2 g, that is going down. You put the equation together just like you did before. Vertical forces, n is upward, mg is downward. Mg you just found it's 637, correct? I'm not going to replace the mg just yet. I want to keep it the way it is. This is negative 0.2 g times m. Okay, let me write it down as ma first. N minus mg. Now A is negative 0.2 g n minus mg. The left hand side becomes minus 0.2 mg equal to n minus mg. N would be equal to mg minus 0.2 mg. Good? Right? I didn't do anything which is not explained clearly here. I have just kept everything in the form of mg. Mg is the actual weight, how much it is reduced by this 0.2 mg. You subtract them, right? Plug in m, plug in g, get the value for n. Tell me what you get. Right? And this is .8 mg is going to be less than mg. Is that 5 or 9? Okay. that is the weight, apparent weight in the elevator, and that's a normal force. If the question asks you what's the apparent weight, it's asking you for the normal force. If the question directly asks you what the scale reads, it's asking you for the normal force. The question can ask you directly that what would be the normal force when she is accelerating downward. Yes? 1 minus 0.2. So even if you don't follow the same way I did it, you could plug in all the numbers here, all the G's, all the M's, you will still get the same answer. Okay? But in physics, usually we go through the symbols as long as we could. Okay? Symbols are they are very important language. So next is the what's the time? 2 minutes, right? 1 minute? How about 2 minutes? Okay. I'm stopping.